Okay, so we have, this is the perpendicular side, the point E. So we have two right angle triangles, BGF, and right angle triangle BEF. This is the angle R, angle of refraction. So this is the refracted ray. Now, I want you to tell me what this angle is. Look at this angle. I mean this angle, what is it? What is this small angle? If this is R, okay, and when I extend the normal here, you use this to relate. So when I extrapolate this normal here, you have this ray along this side. So it means that this remains the angle of incidence I over here. So class, if this is R, what will be this angle? I want one of
I minus R.
So what is that? What's the name given to that angle? What's the name given to that angle?
Angle of deviation.
Angle of deviation. That's the angle of deviation. Let's represent it by the symbol sigma. Once the whole height of the prism is h, it means from this side, BG is also h. Please, is it understood by all? All right, so sigma, which is the angle of deviation, is equal to I minus R. Angle of incidence minus the angle of deviation. Now, when you consider triangle, considering triangle BJF, when we take the cosine of R, cos of R, cos R, yes, somebody to help me determine cos R from triangle BGF. Yes. What will be cos R from triangle BGF? Oh, quick. Who would answer for me?
Opposite over H.
Come again.
Opposite over H.
Cos R. Open your eyes. Cos R. Josephine. Appear. Let's be fast in our response. Cos R.
H over opposite.
H over what?
Opposite.
Appear. Cos is adjacent over hypotenuse. Open your eyes.
So the H over the line BF.
Exactly. So cos R would be equal to adjacent H over the line BF. Okay. Now, our bone of contention is that we want to look at, you see, this is the original direction of the incident ray. Now, because of difference in density, it is deviated. The straight line of the angle of incidence is deviated to line BF. So, the reason for which this angle is the angle of deviation. Now, we want to see how the ray has been displaced from its original path. This is the original path. Now it has been shifted to this side. So we want to determine the distance FE. Let's represent FE by the symbol D. We want to see how the ray has been shifted laterally or displaced laterally. Okay, so let's find cos of the angle of, sorry, the sine of the angle of deviation. Sine of the angle of deviation. Sine sigma. Dojua, help us determine sine of this angle. Aboye, Kenneth, Josephine, Janice,
Sir,
Inshira, Equia, Dojua. Yes. Sine of this
sir,
angle.
please, sine of sigma is opposite on hypotenuse. That is line FE on line BE. Sorry, line yes, sir, line FE on
Okay.
line BE.
All right. And FE is represented by the letter D. So D over BF. Right? Now, let's make this sigma is I minus R, which is this. So sine of I minus R is equal to D over BF. From this equation, and then the sine equation, let's make BF the subject from each one of them. So, Janice, help me make BF the subject from equation 2. This is 1, 2, this is 3. Janice, help me make BF the subject. BF. Just make BF the subject from equation 2.
Cos R over H.
So, Janice, look at it again. BF is a denominator. So when you cross multiply and make BF the subject, it won't be the same. Janice, I'm waiting. BF will be equal to
H over cos R.
exactly. So H over cos R. Then, Oye, help me make BF the subject from equation 3.
Please, D over sine I minus R.
Thank you. So BF D over sine I minus R. BF meaning they all share a common hypotenuse. Triangle BGF, triangle BEF, they all share a common hypotenuse. So we can equate them. H over cos R is equal to d over sine I minus r. Help me make d the subject. Help me make d the subject. And Kenneth.
So please, D is equals to H over cos R times sine I minus R.
So d would be equal to h times sine I minus r over cos r. This d is what we call as a lateral shift. Lateral shift or displacement or lateral displacement. Why lateral shift or lateral displacement? Originally, the incident ray is supposed to just go straight. But because of the varying densities, its path is shifted to BF. So if you want how much it has been shifted horizontally, that is what we technically call as lateral. You are biology students, so lateral. If you want to get how much it is shifted horizontally, that is the expression for D. Okay. Now, if you want to determine the refractive index of the rectangular prism, it is still the refractive index, of course, absolute. That is the real refractive index of a material. Ishra, can you hear me? Ishra? So the refractive index is still sine of the angle of incidence I to the sine of the angle of refraction R. The value remains the same. This, in fact, you do this in practicals. In practicals, you see, you'll be given a certain angle of incidence. There's a rectangular prism. You'll be given an angle. Maybe an angle of incidence of 30, different values. I starting from 30, maybe 15, 20, 25, 30, and so on and so forth. So after measuring this angle, you draw the incident ray. You draw the incident ray, then measure the angle starting from the least one. Then the next procedure is that you put 2 pins along the incident ray. So pin 1, P1, maybe about 5 centimeter interval, P2. So these are 2 pins. What I'll do is that I'll be performing the practicals step by step and then upload it on the platform for you to see how I went about it. I think it will help. So after placing the 2 pins on the incident ray, You view through the other side of the glass block. So assuming this is a glass block, you draw the normal here to the interface, draw the angle, put 2 pins. Then you view through the glass block from the other side, meaning this opposite side of it, to trace the image of these 2 pins. So when you look through it, you see these 2 images in a straight line. So you try to put 2 other pins at the other side so that it will match these 2 that you see as straight pins, okay, at the other side. So when I look through, I'm placing 2 other pins here so that it will exactly match. The 4 will be in a straight line. Maybe this one and then this one over here. After that, I join. This is P3, P4. When you join these 2 points, then you join this point to this point. Then you can determine how the ray, the incident ray seems to be shifted from its original path, the lateral shift or displacement G. Okay. As for every angle of incidence, you determine the angle of refraction because you use information on I and R to determine the refractive index. So the follow-up can be plot. You then plot a graph of. So after determining I, after I will be given to you, but after determining the corresponding R for each one of them, you'll be asked to find sine I, and sine R. Okay, then you'll be asked to plot a graph of sine I against sine R, or the other way around. So a graph of sine I on the vertical and sine R on the horizontal. This will give you a straight line. You'll be asked to find the slope. Now, class, if you are to plot a graph of sine I against sine R, what do you think the slope of this graph would give you? What will the slope of this graph give you? Yes, anybody?
The refractive index.
Exactly. So the slope of this graph, which is sine I over sine R, must be equal to the refractive index of the glass block, maybe 1.5. So the refractive index of glass is around 1.5. So if you conducted the right experiment, you get a value close to 1.5. If it's about sine R against sine I, then the slope will be the inverse of the refractive index, which is 1 over 1.5. Please, are we okay?
Yes, sir.
Yes. Are we okay? Is there any question? All right. Then let's apply this in solving a question. Give me a minute or two to get a question for you quickly. Then we move on. So A ray of light strikes a flat block of glass of refractive index 1.5 of thickness 2.00 centimeter at an angle of 30 degrees with a normal. Trace the light beam through the glass and find the angles of incidence and refraction of each surface. Then, okay, so you answer question 11 later. Let me drop the actual question which goes with this concept. The question 11 is about what we did yesterday and all that about absolute refractive index and the other refractive indexes. So I just dropped a new question. Let's look at question 16. Question 16. Please, are you there? Are we there?
Yes.
Okay, so question 16. When the light illustrated in figure 35.16, P35.16, I'll send that figure to you, passes through the glass block, it is shifted laterally by the distance d. If n, which is the refractive index of the glass, is 1.5, what is the value of d? What is the value of d? Then the 17, find the time required for the light to pass through the glass block described in problem 16. So let me give you that figure, that diagram which goes with this particular question. All right, so I've sent the diagram. So when the light illustrated in the figure passes through the glass block, it is shifted laterally by the distance d. If n is equal to 1.50 and n is the absolute refractive index of the glass is 1.50, what is the value of d? Then 17, find the time required for the light to pass through the glass block described in problem 16. I want you to give it a try. Give it a try. The d is about this lateral displacement d, which we've just gone through. So first, you have to use the information given to find the lateral shift d. When you finish, you calculate for the time required for the light to pass through the glass block. So 5 minutes to give it a try. Let's see what you can do before we look at T. Start with. With a value of D, hello, have you found the value of D? Hello.
Sir.
Are you through with D? Or none of you is through with D?
Sir.
What did you make for D?
0.4 centimeters.
0.4.
Yes, sir.
Josephine, what about you? Inshira,
Please,
what
I
about
has
you? Mhm.
please, I has 0.388 centimeters.
Oh yeah, what did you also make for D?
Please, I had 0.38 centimeters.
Let's see. So, of course, this is R. So the usual concept is that the lateral displacement D will be equal to sine of sigma, which is this angle, over cos of the angle of refraction times the width of the prism H. Okay, H is known. This is it. Sigma S I minus R. We don't know R, so but we have I. So how do we find R in order to subtract it from I? Yes. Don't you ask? How do we find R so we can subtract it from I to get the angle of deviation?
Sir, please, the absolute, we use the Snell's law, which is the absolute refractive index is equal to sine I on sine R.
Fantastic. Fantastic. So we are given the absolute refractive index. So using Snell's law, this were given as 1.5. Is equal to sine of 30 over sine of R. Therefore, sine R is equal to 0.5. Sine 30 is half over 1.5. So this is 1/3. So sine of 0.3333. Therefore, R is a sine inverse of 0.3333. And what's the value of R? Sine inverse of 0.333.
19.45 degrees.
So 19.45 degrees is R. Now, once we have R, we can easily find the angle of deviation. Therefore, sigma is 30 minus 19.45, which is equal to
10.55.
10.5.
10.5.
55.
Did you say 10.5?
Yes, please. 55.
Okay. Okay. Then The lateral shift therefore will be equal to 2 centimeter times sine of 10.6 divided by cos of 19.45. What will be D?
0.3
0.3,
centimeter.
0.38. All right. Then the next question. Determine the time required for the light to pass through the glass block. Yes. How do we go about the next question? 17.
Sir, please, we
Yeah.
can use the other formula for refractive inverse.
And what is
That
that?
is the speed of the light in the first medium over the speed of light in the second medium.
Mm-hmm.
Velocity in the second medium. And then we know that velocity is equal to distance over time. And here our distance is the h. So we just make t the subject.
So Kenneth is saying because V is equal to S over T, T is equal to S on V, and we have S to be 2 centimeters. So when we get velocity of light in the material, we can find the time. Please, do we have a different view? So all that Kenneth is saying is, let's use this C on V to find V, C on N, which of course will be 3 times 10 to the power 8 over 1.5, which I agree. So Ken is saying we just would have to divide this 2 times 10 to the power 8. And that will be for T. Do we have any other view? Or we all agree with the suggestion made by Ken? Akuya, Janice, Oye, Josephine, Inshira, do we all agree with this approach, or you have an alternative view? Nobody is talking. Do we agree or not?
Yes, please.
I also have a different view. My concern is that the distance traveled by the time is not 2. Even though the speed of light in the material, I agree with it, absolutely. But the distance traveled by the time, I disagree. This is the reason. Please, the light, looking at the diagram, the light did not go through the prism direct. This is the path of the light. So this has to be the distance. traveled by the light within the prism. Please, are you okay? If you are saying that the distance traveled by the light is 2, then what you are saying is that the light went through it straight, vertical. But this is actually the path of the light, the refracted ray within the prism. So if you are looking for the distance, it is from this point to this point. Please, do you agree with me?
Yes,
Class,
please.
class, I'm asking you a question. Are you okay with the explanation?
Yes, please.
So if you are looking for, get the value of this distance. Do we have it? Do we have that distance?
Yes, please.
All right, then use it. Let's see. Substitute it into the relation. Let's see what you can make for the time again. So find this distance and then substitute it here. Let's see what you'll be able to produce as the time. Okay, so using, once you have R and we have the adjacent, if we use cos of R, cos R is the adjacent, which is 2 over this distance hypotenuse. Let's represent this by P. So the adjacent is 2. R, we have it. R is 19.45. Therefore, P, which is the hypotenuse, will be 2 over cos of R. So 2 divided by cos 19.45. So divide 2 by cos 19.45. Yeah, just what's the answer? 2 divided by cos 19.45.
2.12 centimeters.
2.12 centimeter. So that is the distance traveled by the light within the prism. Therefore, the time, which is S on V, now we can also directly divide 2.12 by the velocity of light in the material. We had 2 times 10 to the power 8. We can divide this 2.12 by this. This is because 2.12 is in centimeter. So we must convert it to meter before. This is because the speed of light is in meter per second. So we must convert the distance to meter in order to use this. Okay. So 0.0212 divided by 2 times 10 to the power 8 would give us the time. So point and then give me the final results. 0.0212 or 2.12 divided by 2 times 10 to the power negative 10. I think that would be ideal. 2.12 divided by 2, which is 1.06. This is 1.06 times 10 to the power negative 10 seconds will be the time taken by the light to travel through the glass prism. Class, is everyone okay? Is everyone okay?
Yes, please.
Yes, sir.
All right. So this is an application of uh apparent refraction of light in a rectangular prism. I'll look for questions as usual on this and then give you. But as I said, it has this practical application. It has this. And one other thing, before we continue, let me draw your attention to one other thing. Yesterday, we learned that whenever there is refraction of light at parallel plane, angle of incidence equals the angle of emergence. Look at these two sides. These are two horizontal parallel sides, plane. So when the light emerges and you draw another normal to this boundary where deviation would occur over here, you see, because the light incident within air passes through the prism and emerges through air. Refraction of light at parallel plane, you have this angle of incidence being equal to the angle of emergence. So when the light is emerging out of the prism, the angle of emergence E equals the angle of incidence I. Oh, my mark. So we'll have I being equal to E. Why? Because this is refraction of light. The reason is refraction of light at parallel plane. Parallel plane. So when the two planes are parallel, then the angle of incidence at the other end is equal to the angle of emergence. So E would have to be 30 degrees. All right. Let's look at real depth and apparent depth. Height. Real depth and apparent depth. Also under the same concept of refraction of light. real death and apparent death. And apparent death. I don't know if you've been that observant, but during sunny days, when you visit the pool, during sunny days, and especially not only the pool, but when you, visit a nearby river during sunny days, or in the aquarium, if you've seen an aquarium before, on sunny days, if you look at fishes swimming in rivers or in aquarium, you always it always appears as if the fishes are closer to you than in real situation. So I remember when we were kids and then visited the stream and then the river during hot afternoon, because per our view, we think the fish within the pond or the river seems to be so close to us. We want to quickly dip our hands into it to catch the fish, only to be deceived. The same phenomenon also happens when you drop a coin in water and then place it within an open space. When you look through the water to look at the coin under there, you realize the coin seems to be closer, or the bottom of the basin or the bucket always seems to be closer, shallow. Please, have you any one of you made such an observation before? Hello?
Yes, please.
Yes, please.
So the pond always looks shallow, or the bottom of the basin, the bucket always looks shallow. And this is an optical illusion. This observation is an optical illusion. So I remember when I was a kid, I was once deceived by this illusion, and I fell into a river with that huge force on me, because I felt, oh, the bottom was just here, only to dive and realize that it was rather so deep. This is an optical illusion that happens during refraction of light. Okay. And it is based on the fact that when light travels from a denser medium into a less dense medium, there's always deviation, either a denser medium to a less dense, or less dense to a denser medium. There's always that deviation. So it seems to shift the ray, or the ray of light vertically. So let's take this to be a basin. Let's take this to be a coin or a pebble. under a basin of water. Now, whenever light travels perpendicular within the same medium, its part is never refracted. When light travels perpendicularly through a medium, so this is light coming from the object, but it is going perpendicularly. Once it is, the path of the light is perpendicular to the surface, it goes undeviated. Now we see, as a result of reflection, before an observer appears, can see the object here. Light would have to travel from the object to the observer's eye. So if you are here and you are looking at this object, light would have to travel from the object and be captured by you. So this is the light coming from the object. This light is traveling perpendicular to the surface, so it goes undeviated. This is another light at an angle, acting at an angle. So let's bring the observer rather here, as if he or she is observing from this angle. This is because the light would have to come from both angles. So this is another ray coming at an angle to the observer. Now, whenever light travels in this manner, when it gets to the interface or the boundary between two different media, air and water, what happens to it? What happens to this ray? What will happen to it? Plus, what happens to this ray?
To refract.
And how will it refract? This is a normal. So how will it refract or bend?
This away from the normal.
So it will bend away from the normal because it's coming from a denser medium to a less dense medium, which is the air. An image will always be formed whenever two or more refracted rays meet. An image is formed when two or more refracted rays meet. Now look at these two refracted rays. This one, and this one. There's no way they'll ever meet in front here. So to form the image, the object, this refracted ray is extended backwards, prolonged. So where it appears to meet this ray becomes the virtual position of the object. Becomes the virtual position of the object. Yes. So this is the object, and this becomes the image. So this is exactly what happens whenever an object is in water and somebody is looking at it from outside the water medium, we can also do the same thing using a different approach. This is a basin of water. An object is here. Now, this time the observer is looking at the object directly downwards here from direct above the basin or cup. So we have, there will always be a lot of objects, light coming from an object. So one of the light is such that it is traveling perpendicular to the surface. And whenever light travels perpendicular to the surface, it goes undeviated. Then another light from the object at an angle. When the light gets to the interface, let's use 3 rays. That's how we make a class. I'm reading them in fair way. David. All right. Okay, so when these two lights gets to the boundary, they will deviate, but the deviation is that they will deviate away from the normal. This one would also deviate away from the normal. This one would also deviate away from the normal. They will deviate away because the light is coming from water to air. So this is the refracted ray. This is the refracted ray. And as you can see, 1, 2, 3 refracted rays are never meeting. An image will be formed when 2 or more refracted rays actually meet or appear to meet. If we look at 1, 2, 3, there's no way they will ever meet up here. And so we have to retrace their path. Where they appear to meet would be the point where the image will be formed. So this becomes the object, and this becomes the image. So an observer up here sees the image of this object as if, or sees this object as if it is here. And that is the optical illusion whenever we look through a denser or water when there is an object down there that is being viewed. It can be fish, it can be coin, it can be stone, anything within water. When you see where you think the object is actually the image. Is due to this illusion. Okay, so under this concept, the distance from the surface of the water to the real position of the object becomes the real depth. So this is the actual or the real depth. And from the surface of the water to the apparent position of the object, or now the image becomes the apparent depth. So if, let's label maybe A, B, okay, A, B, this point B, C, and D. The distance BD becomes the real depth, height. That is height. And then the distance BC is the apparent depth. So if this were to be fish in an aquarium, when you look at this fish up here, it would appear to you that this is the position of the fish. So you dip your hand to this level to catch it, and it is well dodged because this is the actual position. But due to refraction, you are seeing it to be here, and the fish would always swerve you. So it takes experienced people to always catch fish in water. Please, is that okay? Are we
Yes,
okay?
please.
All right. Now, let's determine, you can use this concept to find the refractive index. You can use this concept to determine the refractive index of the material or of the water. Okay. This angle, let's say this angle is I. And this angle, of course, this is angle of refraction. By corresponding angle point of view, this angle also corresponds with this angle. So if this is I, this R, this will also be R. Or by vertically opposite rule. If this is R, this is also R. And this angle would also alternate with this angle. So once this is R, this is also R. Okay. We know refractive index to be sine I on sine R. So if we consider this triangle, consider triangle ABD. ABD is a right angle triangle. The right angle triangle ABD. When we take sine of this, sine I will be equal to AB over AD. AB over AD. And then when we consider triangle ABD, ABC, we're considering triangle ABC. ABC, sign of R. Sign of R is also equal to AB over AC. This sign R is opposite AB over AC. Now, you see, the principle behind this is that we are assuming that by normal approximation, what do we mean by normal approximation? By normal approximation, we are taking angles I and R to be very, very small, to be very, very small angles. So if we take small, very, very I and R to be very, very small angles, then sine I is approximately equal to tan I, and sine R is approximately equal to tan R. So instead of sine I over sine R, we will equate this to tan I over tan R. This is because we are considering normal approximation where I and R are very, very small. So let's find tan I from our diagram. The same way we determine sine I, we consider triangle ABD. So if we take tan I will be opposite AB over BD. So AB over BD. Then tan R will also be AB over BC. AB over BC. So by normal approximation, we are equating tan I and tan R for these two, meaning there. Let me clear this diagram. Meaning the refractive index, absolute. The absolute refractive index would be tan I is AB over BD. Then tan R, so over all times BC over AB. Please, are you with me? Are you following up to this stage?
Yes.
Hello, are you following up to this stage? Are you there?
Yes, please.
Okay, so this and this cancels, and we have BC over BD. Now, look at this refractive index thing. We are looking at, if you take refractive index and it is sine I over sine R, then it means we are moving from air to a denser medium. So this is actually air to maybe water. But look at what we've considered. We were looking at from water to air. So it means that whatever we've had, okay, wouldn't be, it's actually the inverse of this. Okay, we pick this as, we use n is equal to sine I over sine R. Now, from what we are doing, this is actually from water. Okay, so what we are actually doing, which is this is the inverse of water to air. Our refractive index, as we are considering, will be from water to air. So N from water to air is what we have had, which is BC over BD. If we want real refractive index, then real refractive index, which is 1 over, okay, will be 1 over whatever we've had. Or refractive index from air to water is actually 1 over refractive index from water to air. So if we want real refractive index, then it will be, we had from water to air to be BC over BD. So we'll have 1 over BC over BD, which is BD over BC. So the absolute refractive index from air to water would be BD over BC. Now, from our diagram, what is BD? BD is the real depth. Real depth over BC. BC is the apparent depth. And so, whenever an object is dropped in water, the refractive index of the water or of the liquid N can be determined by its real depth over its apparent depth. So that is how to determine the refractive index of an object dropped in water. The absolute refractive index of the liquid or of the water becomes the actual depth over the apparent depth. Now, the apparent depth is this distance, BC. The real depth is BD. Now, when we subtract apparent depth from real depth, so real depth minus apparent depth, this is equal to the vertical shift. You see, the object was here. the object is here and it appears to be shifted vertically to a new position at C. So when you subtract the apparent depth from the real depth, you determine the extent to which the object is shifted vertically. And we call this vertical shift or normal shift. Normal vertical shift is equal to, this is equal to the real depth RD minus the apparent depth AD. So the vertical shift, the normal shift or vertical displacement is equal to the real depth minus its apparent depth AD. Please, is that okay?
Yes, please.
All right, so take note of things to look at: the expression of the refractive index, and then the expression of the vertical shifts. Okay, because that is what we'll be using to solve the problems involved. In our next meeting, we will go through how we derived the formula for the refractive index from it again, and then the vertical shift and the normal shift, then use it in solving problems. Then we continue, okay, to refraction of light in triangular prisms. Please, if you have any question, ask, because we have just 3 minutes to clock 9 o'clock. If you have any question, ask. If you don't have any question, then we end. Akuya, Josephine, Donchua, Janice, and Co.
Is it that there's a light source at the bottom of the water, which like will move from
No,
center to
object. Akuya, you are swimming in water or in a pool, and somebody is looking at you from the top of the water. So this thing, this spot here is you. The observer is this eye watching you from the water. Okay, so how the observer will see you? So this is the object, you. This is your image, which will appear to the observer. So even though you are here, but the observer will be deceived to look as if you are here. Are you okay? Okay, are you okay? Maybe a line is not stable. Please, any question? Josephine, any question? Kenneth, any question? All right. Then let's call it a day. We'll continue on Tuesday. Good night to all of you.
Good night.